Math 1314, Chapter 6, Matrices and Determinants, Section 1, Matrix Solutions to Linear Equations, Video 2, Matrix Goal Number 1, Row Echelon Form. In the previous video, we talked about rewriting a system of equations in something called an augmented matrix. And the idea of it was to focus solely on the numbers in a system of equations and their positions and kind of put the variables to the side with the intent of bringing them back in at the very end. In this video, we're going to talk about what one of our goals would to achieve with these matrices called row echelon form. So let's start by defining that. A matrix is in row echelon form if it meets the following conditions. Number one, the first non-zero entry in a row is 1. Such an entry is called a pivot. And number two, every entry below a pivot is 0. Now, this is actually much easier to see than to put into words, but basically what it's saying is when we look at a row of numbers, the first number that isn't 0 needs to be a 1. And whenever we see one of those initial ones called a pivot, every number below it must also be a 0. Normally, this results with a matrix with 1s on the diagonal from the top left corner downward with 0s below that diagonal. Let's take a look at some examples. The following matrices are in row echelon form. In the first matrix, notice that the first number in the first row is 1. And so that is the first non-zero entry in that row, and it is a 1. Look in the second row. The first non-zero entry is a 1. And look in the third row. The first non-zero entry is a 1. So the first criteria is met where the first non-zero entry in a row is 1, and those entries are called pivots. So in this matrix, the 3 numbers highlighted in yellow are called pivots. But additionally, look at criteria number 2. Every entry below a pivot is 0. Well, if you look below each of these 1s, below the first one are nothing but 0s, and below the second one are nothing but 0s. And again, we kind of have this diagonal of 1s cascading from the top left corner downward with 0s below it. It's not always a perfect diagonal, as is illustrated in the second example. First, let's make sure the first non-zero entry in each row is 1. In the first row, the first non-zero entry is 1. In the second row, the first non-zero entry is 1. And in the third row, the first non-zero entry is 1. And notice below each of the pivots that are highlighted in yellow are nothing but 0s. 0s here and 0 there. Now, if you're wondering why is this a 0, well, it just is. I know it's below the 4, but to be in echelon form, row echelon form, every entry below a pivot must be 0. All right, so those are examples of matrices that are in echelon form, row echelon form. So what are some examples of matrices that are not in row echelon form? Well, let's take a look at these examples. In the first matrix, the first row, the first non-zero entry is 1. And in the second row, the first non-zero entry is 1. And in the third row, the first non-zero entry is 1. So it satisfies the first criteria that the first number in each row that isn't 0 is a 1. However, the second criteria says every entry below a pivot, below one of the ones I have highlighted, must be a 0. Well, under the first one, every entry below it is a 0. But we can't say the same thing for the second pivot. We can't say the same thing for this pivot right here, because below it is a number that's not 0. So this is an example of a matrix that is not in row echelon form, meets the first entry, first non-zero entry being 1 criteria, doesn't meet the everything below those 1s equals to 0 criteria. So not in row echelon form. What about the second matrix? Why is it not in row echelon form? Well, it's probably pretty obvious because the first non-zero entry in each row is not 1. The first non-zero entry here is 2. The first non-zero entry here is 3. And the first non-zero entry here is -1. Now, if you overlook the fact that those weren't 1s and only looked below them, then yeah, it meets the other criteria that everything below those quote unquote pivots are 0s. But the first non-zero entry in each row is not 1, and that's why this one is not in row echelon form. These are not 1s. Now, you may be wondering, is there a way to fix these problems? The answer is yes. Because if a matrix is not in row echelon form, there are moves that we can do to get them in row echelon form, which leads me to the next slide. Actually, it leads me to the next slide after that. How can we convert an augmented matrix for a system of equations into row echelon form? We'll answer that in just a second, but I want to show you the advantage of an augmented matrix being in row echelon form. The advantage to being in row echelon form is it makes the system easy to solve. If you view this as an augmented matrix, meaning that it came from a system of equations, we can put it back into a system. Assuming that the variables were x, y, and z, the top row would represent 1x plus 1y plus 2z is equal to 19. But what equation would the second row represent? Be careful, it starts with a 0. Assuming the columns represent x, y, and z, there are no x's. There's just 1y and 2 z's equals 13. Well, what would the bottom row represent? Well, the first 2 zeros mean no x's and no y's. And then the 1 in the third column right here means 1z equals 5. So the advantage to a matrix, an augmented matrix representing a system being in row echelon form is you already know the value of one of your variables. The bottom equation says z is equal to 5, but it goes deeper than that. Because now that I know what z equals, I can go to this equation, which doesn't have any x's. Back substitute the z, get y plus 2 times 5 is equal to 13. And without dilly-dallying, if you solve that, you get y equals 3. And just like that, we've got 2/3 of our solution. But now we can go back to the top equation, put in the z and the y, and that would give us x plus y, which was 3, plus 2 z's, which was 5, is equal to 19. And again, without dilly-dallying there, if we solve that, we would get x equals 6. So if you have an augmented matrix that represents a system of equations, and it's in row echelon form, then you can finish solving it real fast because the bottom row will probably tell you what one of your variables equals. You can back substitute upwards through the rows or through the equations the rows represent and get the other 2 variables fairly quickly. So going back to the original question before I did that, how can we convert the augmented matrix for a system of equations into row echelon form? And the answer is using something called row operations. So in the next video, we'll talk about moves that we can do to an augmented matrix or a matrix in general that will transform it into a new matrix without altering the solution to the system that it represents. And there's only 3 row operations. For the most part, they're pretty easy. It's the third one takes a little bit of thought. You'll see.